So just to recap briefly what we did yesterday, we focused on deriving equations of motion for a rotating body and relating the rate of change of the angular momentum vector to the rate with time to the rate of change with time to the angular momentum vector in a stationary system, which led up to the Euler equations. And the Euler equations weren't, in their most general form, straightforward, because they were, okay, granted they were first order differential equations, but they were non-linear because we had second order terms of omega. But we saw that in the special case of a symmetric body where you had two main moments of inertia that were equal, we could actually solve the equations analytically and saw how this gave rise to precession. So we'll continue today with another example of how rotational motion may look like. And this is a pretty cool effect, actually. It's a gyroscope effect. And so the situation we're considering looks something like this. So you can imagine that this is a bicycle wheel, which has been attached to a rod here that is suspended here. And it's suspended in such a way that it can rotate freely. So the wheel is free to just spin around its own axis and also rotate freely in any direction as it has been attached to this point here. So the wheel has a radius large r, and it's rotating, spinning around its own axis with an angular velocity of omega s. And we also have gravity acting on the center of mass of the wheel with a force mg. We're considering a coordinate system like this. So we have the x-axis along the rod here, which has a length d. And I'll tell you right away what we will show. We'll actually show that when this wheel is spinning around its own axis with an angular velocity of omega s, it will lead to a precession in this horizontal plane of the wheel. So the entire rod here with a wheel attached to it is going to precess in the plane. This might seem a bit funny, because imagine if this wheel had no angular velocity. Imagine that omega s was 0. So you have a wheel attached to a rod attached to this point. So I'm basically, let's say I'm holding the wheel here. Let's say I let go of the wheel. What would you expect happens? Falls down. There's nothing preventing it from just dropping. So the difference here is that now I'm holding the wheel, but I'm spinning it. Let's say I can spin it really fast. So I'm giving it an initial angular velocity. So it's now spinning, and now I let go of the wheel. Seemingly magically, the wheel is now not dropping. Instead, it's going to rotate. So the wheel seems to be defying gravity, levitating. So we'll see what happens. So in order to get an idea of what the rotation looks like, we have to find some way of identifying the time evolution of either the angular momentum or the angular velocity vector describing this wheel's rotation. Because we need the time dependence to be able to predict what will happen as time evolves. So we'll start by considering the angular momentum. Well, first of all, the angular velocity vector is given like this. It's pointing in the x direction. And if you recall yesterday, we discussed that there was, since the matrix of inertia, this I matrix, is a Hermitian matrix, it's always possible to diagonalize it, meaning that we should be able to identify a preferable coordinate system where this matrix of inertia is diagonal, with the main moments of inertia along its diagonal. And in this particular case, for a highly symmetric body, it's quite intuitive, I would say, what this preferable coordinate system is. It's simply the coordinate system in the plane of this wheel. And you can show this mathematically if you want. But just imagine that you have this wheel, and so you can choose the coordinate system in a way that it fits most symmetrically with the body. And that's most likely going to be your preferable coordinate system. And this is precisely the coordinate system here. So from this figure, it might not be obvious, but the wheel is then actually located like this. So the x-axis here is normal to the wheel. So in our particular chosen coordinate system, the matrix of inertia, the matrix indicated by this underscore, is given like this. So what would you expect for the values of these main moments of inertia? Could you say anything about their magnitude related to each other? Okay. Yeah, exactly. So you're basically exploiting the symmetry of the wheel to say something about the magnitude of the moments of inertia. Yeah. Now, keep in mind that we derive the general relation between L and this angular velocity vector. Now, since the matrix of inertia is diagonal, it means that L has to point in the same direction as omega here, since omega only has an x component. So L should also be directed in the x direction, which makes sense. The wheel is rotating like this, okay, so the angular momentum with respect to this point is along the x-axis. So the angular momentum should be given like this. And now we can ask, what is Ix? Well, we have a general formula for calculating it, which we derived in the previous lecture. And the formula would look like this. The form we wrote down for this formula was dV, I think, and then rho, the mass density, times r squared minus x squared. But we're just shortening down the notation here so that dm is rho dV. So we have to consider the figure here. R is then the position to each mass element of this wheel, and the x is the distance to this element along the x-axis. So we see then that r squared minus x squared is given by large R squared, just by forming this triangle. So we get this formula. So the moment of inertia around the x-axis is just given as the mass multiplied with the radius squared of the wheel. So we have the following formula for the angular momentum associated with this rotating motion of the wheel. Now, I stated that in order to say something about what happens with this system, how this system evolves with time, we have to find some kind of equation of motion for the angular momentum. We have to find some equation from which we can extract the time dependence. And one way to do so is to use, this. This is just a definition, but it's also a first order differential equation, right? So if we're able to identify the torque acting on the wheel, then we know that this has to be equal to dl dt, so we can just integrate the torque over time to obtain L. So can we say something about the torque? Well, the torque on the wheel originates from forces acting on it. We have one force acting on it, gravity. So gravity leads to a torque of the wheel around this suspension point. And one approach in order to identify the torque acting on this wheel could be to, like we've done a number of times, just divide this wheel into several subregions, each with a mass dm, and then consider the total torque by summing all of these masses. But from previous calculations, we know that the force acting on this wheel should be equivalent to a force acting on the center of mass. Now the torque is given by R cross F. So we get this. The force acting on the center of mass is mg in the minus z direction. And the position vector to the center of mass is dx unit vector. So you would get the same result if you just consider the torque acting on each sub-region of the wheel. This is equal to mgd acting in the direction of y. So the torque is acting in this direction, which seems reasonable in light of the fact that we stated initially that gravity will try to pull, if this wheel isn't spinning, gravity will always try to pull this wheel down. And if the wheel is going down like this, well, that's an angular momentum like this. So the torque is trying to shift the angular momentum in this direction due to gravity. And of course, it does the same thing even if the wheel is spinning, but it has a different consequence compared to if the wheel is not spinning, as we will see. So the change in the angular momentum of the wheel due to the torque is given like this, just following from the fundamental definition here. All right, so we see that the change in angular momentum is parallel to the torque. But the original angular momentum was pointing in the x direction, and the torque is acting in the y direction. So the angular momentum and the change of the angular momentum are perpendicular to each other. And if we then consider the same scenario after the wheel has been shifted, the same thing occurs. So the torque will always be perpendicular to the angular momentum. So what can we conclude from this about how the angular momentum vector evolves? Well, we have a vector, and then we have the torque causing it to change like this. It's always acting perpendicular to the vector. So we should get a circle. This means that LS is basically rotating in a plane. So let's try to sketch this scenario. Imagine that this is the XY plane. So we're looking at our setup from above. So the wheel is like this. Initially, let's say we're considering the angular momentum at some time t. Now we know that the torque attempts to shift the angular momentum in the y direction. Like this. So the angular momentum at a later time, delta t, should look like this. And we will get the same thing at all points in this curve, because the rate of change in the vector is always parallel to its present location, which means that we get a circle, while the magnitude should remain constant. So from this we see that the change in the angular momentum should be equal to its length multiplied with the angle it subtends here during the time delta t. Delta t. If we now divide this equation on time and let this increment in ls become an infinitesimal, we get dl dt So I'll now name this angular velocity here large omega. So it's the rate of change of this angle. And now we have an expression for ls over there. So we get this. And now we also know that the time derivative of the angular momentum is related to the torque. And I'm keeping the absolute value sign here since I have it on this side. And the torque is given as mgd. And so by equating these two lines here, we can isolate large omega, the precession frequency, and it's given by the following expression. It depends on the gravitational acceleration, the length of the rod, the radius of the wheel, and also the angular velocity of the spinning motion of the wheel. So what we see here is what we initially stated. The angular momentum of the wheel is rotating in a circle, which means that the wheel is rotating in a circle. And apparently it seems to be levitating. It's not falling down, even if gravity should be pulling it down. So we have to think now, why does this happen? Well, it's a matter of conservation of angular momentum, because the torque here is always acting in the direction perpendicular to the angular momentum. So if we start out with having a finite angular momentum, all the torque does is to shift this momentum around in a circle, since it's always acting perpendicular to it. However, I will reveal to you that, as you may or may not have seen, we've done a pretty major approximation here. Because say that we have this wheel, it's attached to a rod to the suspension point. If it's not spinning and I let go of the wheel, it drops. According to this, if I spin the wheel first, it's going to rotate. So let's now say I just give the wheel a very tiny shake. So it's just barely rotating. What would you expect happens?
It should fall down, but with a tiny rotation.
Yes, but it should fall down, right? If I just give it a tiny, tiny spin. So that doesn't seem to be in accordance with this analysis, right? According to this, the wheel should just precess in the horizontal plane. So somewhere hidden in this analysis, we have done a major approximation. Or put differently, this analysis is valid under a specific condition. So please take a minute to discuss with your neighbor what's the approximation here, or condition. So if you have any suggestions, just shoot.
Well, the angular rotation omega s is constant.
Mm-hmm. Absolutely, that's definitely an approximation, because say we have air resistance, stuff like that, friction, omega s should slow down. So that's true, that's one approximation, but if we think about what would happen if you have a bicycle wheel and you spin it, if it's reasonably well greased, for instance, it shouldn't slow down that fast. So it's an approximation, I agree, but it's not a crucial approximation for this analysis. So let me give you a hint. So we had something like this. Omega s. Right, an angular momentum like this. So we said that the angular momentum was given, the angular momentum of this wheel around the suspension point was given by some simple formula, mgr squared omega s, I think, something like this. Is this true? Is that the only angular momentum involved in this?
Well, if you neglect the mass of the
Mm-hmm.
of the wheel.
Yeah, you have to neglect the mass of these. Or did you? No.
Mark on the
All right.
from the wheel.
True. Yeah, we're neglecting that. But is there any other possible source of angular momentum? So we're saying here that the wheel is rotating in the horizontal plane. So that means that if it's rotating, well, then the wheel should also have an angular momentum like this, right? It has some motion in this plane, so angular momentum is pointing up. But we haven't considered that at all. So the wheel is spinning around its own axis with omega s, and it's revolving in this horizontal plane with a speed, angular frequency, large omega. But we have completely neglected the angular momentum stemming from that rotation. So what we have assumed here is that this precessional motion is sufficiently slow that we can neglect the angular momentum originating from it. So basically, if this omega is sufficiently small, then the angular momentum due to this motion will also be small compared to the angular momentum from this spin. So in other words, this analysis is only valid if omega s is much greater than this precessional frequency. And we see that from this equation, a large omega s actually translates to a small large omega. So the more rapidly this wheel spins around its own axis, the slower this precessional motion should be. So the faster we spin the wheel initially, the more correct or accurate this analysis should be. But if we just give it a very small spin, then we cannot any longer neglect the angular momentum from this movement compared to the spin of the wheel. And then what we'll find, if you do the analysis, is that the wheel will in fact drop. So keep in mind that this is valid for this condition. But it's still pretty neat, I think, that you can actually get you can get the wheel to essentially levitate, right? Just from spinning it, defying gravity. I think that's pretty cool. And one thing to note about this equation is that it's actually independent on the mass of the wheel. The mass cancels here. So what matters is the length or the distance to the suspension point and the radius of the wheel, and its spin, of course, and the gravitational constant, but it's independent on the actual mass. So this should work for just as well for light objects as heavy objects. Now we may actually derive this result in a very simple way from another equation, namely the equation that we derived in the previous lecture that relates the time change of the angular momentum in the rotating frame to the time change of the angular momentum in a stationary frame. Namely this. And keep in mind that this is as seen from the rotating coordinate system. So we imagine now that we have a coordinate system which is attached to the wheel. Okay, so let's consider the y component of this. we get this. So with this equation, what I've done now is that I've actually taken into account the possibility of having this Lz, the angular momentum pointing in the z direction, due to the rotation in this horizontal plane. So the angular velocity vector both has a component along the x-axis, which is this omega s, but it also has a component along the z direction if the wheel is precessing this large omega. And similarly, the angular momentum should also have a component along x, this Ls, due to the spin of the wheel, and also potentially Lz. Should be equal to the torque in the y direction. So from this equation, first of all, note that in the rotating system, there is no change in the angular momentum. So we get this formula for the precessional frequency. And by inserting our quantities here, we get this. And so we see that we obtain consistency with the first approach we used in the lowest order approximation, namely where we neglect Lz. So again, it follows from this equation that if we consider a precessional motion that is slow enough so that the associated angular momentum in the z direction is small enough as well, well then we obtain the same result. So there are at least two ways to solve this problem. Okay, we'll have a look at one more example. We'll have a look at a symmetric top, one of these spinning toys, with one fixed point, and see if we can find out something about the physics. So imagine we have one coordinate frame which is stationary. This is just fixed in space. Let's assume the top has some kind of form like this. Perhaps the tip here should be a bit sharper, but the idea is then that this top actually spins on its tip. Center of mass here, for instance. And assume that the distance to the center of mass is given by small l. Gravity acts as if all the mass was concentrated in the center of mass, and the total mass is large M. And so from our previous discussion, we know that we can characterize the rotational motion in 3 dimensions by 3 Euler angles: phi, theta, and psi. So to describe this top in the rotating coordinate system, x, y, z, which is attached to the body of the top, we can just perform one of these orthogonal transformations from the original stationary system to this one, expressed through matrices that depend on these theta, phi, and psi angles. We did this a couple of lectures ago. So what we'll do after the break is to try to analyze the equations of motion describing the system to find out how it actually will move. So we'll take a break.